Okay, we're gonna go ahead and get started and solve this problem today. This is a retaining wall, a pretty good problem for demonstrating the Rankin's theory. So in here what we have is a retaining wall. Right side is in active state, this side, and this side is in passive state. So the question number one is total force on the right side active of the wall, total moment, also the second question is total force on the left side, which is the passive side of the wall. Now first thing we'll do is we're going to calculate, this is the active side, we're going to calculate the Ka, active pressure coefficient. So the active pressure coefficient for the soil is 1 minus sine phi prime plus 1 plus sine phi prime. Sorry about my voice. Now Ka of this soil, 1 minus sine phi prime divided by 1 plus sine phi prime. So 1 minus sine 25, 1 plus sine 25. That is equal to, divided by 1 plus sine 25 is equal to 0.41. So since the same soil we have here, it is Ka of the second soil. Well, it's actually this one kind of soil here, so it's the same. We're going to use the same one. So on the left side, passive side, we're going to need the Kp, which is nothing but 1 over Ka sine phi prime divided by 1 plus 1 minus sine phi prime. In this case, it's the same friction angle, so it's nothing but the same as 1 over 0.41. So the Kp is equal to 2.44. So this is what we're going to use in here. The very first thing that we got to do is to draw the effective stress with depth. Effective stress starts from 0, linearly increases to L level. So let's just extend this line a little bit. And then this point, let's call this level A. So the stress at effective stress at this point is going to be unit weight, which is 115 times the height. Now in this case the height is from, this is 5 feet, so up until here. So up until it's 5 feet, you can see from here, and from here to here is 1 foot. We don't need it. In this side, you can see the water levels are slightly higher than this side. So it's a little bit different from what we saw in class. So 115 times 5, that is going to be 575. So 575 kilopascals. So then let's call this B level. At this point, the stress is going to be 575 plus the height difference between this level to this level, 12 minus, so let's just write this down here. Distance from here to here is 12 minus 5, it's 7 feet. from here to here it was 5 feet. So 7 times, so you want 22 minus 62.4, this is the effective unit weight. So this comes out to be 992.2. This is going to be pounds per feet square. The units are pounds per feet square. Now, as we know, the equation for horizontal stress is Ka times sigma 0 prime minus 2c prime square root of Ka. So c prime is 0 in this level and this level. So as a result, we have essentially Ka times sigma 0. Sigma horizontal at any point will be nothing but 0.41 times sigma 0 prime. So this is true for any depth. So what we're going to do is we're going to multiply sigma 0 with any value that we get. So here what I will do, so it's 0.41, so it's going to go like this, and it's going to be like this also. So this point will be 0. Horizontal here is going to be 0.41 times 992.2. That is going to be 406.8 pounds per feet square. That's this point. So here this point is 575. 0.41 times 575. $235.75 pounds per feet square. So that's this point right here. So so all this is acting horizontally. This is the earth pressure acting from right to left. Now what we're going to do is we are going to also include, since this is the water level that extends like that, we need to include the pressure of the water. So it's linearly increasing with depth. So what I will do is I'm going to just draw with another color perhaps. So here, let's say this is my Z, starting from 0, increasing up until this level, and this is acting horizontally. So this point will be the pore pressure maximum at the bottom, which is equal to 62.4 times, that's unit weight of water, times 7. So 436.8. Now, so we have this triangular load and this trapezoidal load. So what we need to do is we need to calculate in order to calculate the total force, we're going to find the area under all this. So what we need to do is we're going to find the force 1, and we also need its location. So the location, this distance is nothing but the total height of this triangle divided by 3. So this is 5/3, this distance from here to here. So as I mentioned in class, so we need to divide this into 2 components. So the first component will be, we can call it F2, and it will be acting from 7/2 from the bottom. So this is 3.5 feet. So for this one, this is F3, so it will be acting 7/3 feet from the bottom. So the force coming from the water is going to be acting again, something like this. Let's call this F4. It's going to be acting, the distance is going to be 7/3 feet from the bottom. So let's do the math. So F1 is going to be the area on this curve. So F1 is going to be, so the height is 5. This distance is 235.75 divided by 2, that's the area. 235.75 divided by 2 is going to be 589.4 approximately pounds per foot. So the distance from the bottom is going to be 5/3 plus 7. So y1 is going to be 7 plus 5/3, 8.66 feet. So this is the distance from this point at the bottom to all the way to the point where the resultant of the first triangle, which is the F1 acts. So F1 times this distance will give us the contribution of this triangle to the moment, driving moment. So F2 is 7 multiplied by 235, 35, so that is going to be 1650, 25, and y2 is simple. 7/2 is equal to 3.5 feet. So that's distance from here to here. So F3 is going to be 7 times the distance from here to here, which is 406.8, minus this point, 235, 75 by 2. So 7 times 406.8 minus 235.75 divided by 2 will give us 598.7 pounds per feet. So the last one is going to be the location of this one, obviously, is 7/3. 2.33, I apologize for the cough. 4 is this area, 236.8, so 436.8 multiplied by 7 times half, so that's 1528.8 pounds per feet off the wall. So y4 is going to be again 2.33 feet. It's just 1/3 of this whole height. So now we have all the forces and we have moment, arms. We are going to be able to calculate the total force